Okay, we are on to problem number 14. All right, an instrument is thrown upward with a speed of 15 meters per second on the surface of planet X, where the acceleration due to gravity is 2.5 and there is no atmosphere. How long does it take for the instrument to return to where it was thrown? Okay, so here's my wrench. I'm throwing it up, and then it's coming right back down again. All right, what do I know? I know I throw it up with a speed of 15 meters per second. I know here, of course, the velocity will be 0. And I know my acceleration is 2.5 meters per second. It's not 9.8 because we're not on Earth anymore. And no atmosphere, so we can ignore air resistance, of course. So, how long does it take for the instrument to return to where it was thrown? Obviously, when it returns, I know the velocity at this point is going to be the same magnitude, but just opposite in direction. So this is going to be minus 15 meters per second at this point, where the wrench comes right back down to where it was thrown. So what am I supposed to find? Time. I need to know the time. Now I need to know not only the time for it to return from here, but I actually need to know the time for the whole trip. So I need the up and back delta t. Okay, so I got to be careful that I remember to multiply that number by 2 if I'm just solving this part. All right, so let's go ahead and look at what would the velocity time chart look like for this. I'm starting with a positive velocity. At some point it's going to 0 and then it's going negative. So I'm going to have a graph that's going to look like this. Starting here at 15 and then going down here to negative 15 and then of course 0 at this point. I don't know the time. That's what I'm looking for. The time all the way to here. This is what I want right there. But I do know the acceleration, so I know the slope of this line is 2.5 meters per second squared. Okay, so let's go ahead and see. Oh, this should be super easy because acceleration is rise over run. So acceleration is, I can go straight to my definition of acceleration. Do I know the change in velocity? Let's go from this point to this point. So I go from 0 to minus 15. So yes, it's going to be minus 15 minus 0 over delta t, and the value is 2.5, and of course it's negative because it's pointed down. So, oh, I should have done the rearranging there first, shouldn't I? So delta t is going to equal negative 15 divided by negative 2.5, which is, and I'm being lazy, I'm not putting my units in here. Meters per second and seconds. So I get 15 divided by 2.5, which is 6. So from this point where it was 0 to this point down here is 6 seconds. But remember, it doubled, so it was 6 seconds here too. So all total I should have 12 seconds. So the answer should be D, and that is correct. So now let's go on to problem 15, which is problem number 71. So I need to flip to this new page. There we go. Okay, human reaction time is usually greater than 0.1 seconds. If your friend holds a ruler between your fingers and releases it without warning, how far can you expect the ruler to fall before you catch it, assuming negligible air resistance? All right, so let's draw it. This is problem number 15, by the way. All right, so here I am holding the ruler, and here you are. 1, 2, 3, 4, 5. Wow, 5 fingers. And you're trying to grab it. Okay? How far can we expect it to fall? Let's what do we know here? Well, first of all, we know the initial velocity here is going to be 0, right? Do we know the velocity here? No. Do we know anything else? Yes, we know acceleration in here is 9.8 meters per second squared because this is a free fall problem. And we know time. Basically, we're wanting to see how far can the ruler fall in 0.1 seconds. So let's draw a chart here. Our velocity, time. I'm just going to, never mind, I was going to say define down positive, but I don't want to confuse you, so we'll do this. I'm working down here on the negative. Because my velocity is pointing down, it's got to be negative. So I'm starting actually with a velocity of 0, but it's accelerating down, so the velocity is becoming negative. So what I'm looking for is to find at 0.1 seconds what distance has the ruler moved. I don't know the velocity at this point, so what do I know? I know acceleration, as always, and I know time, and I'm looking for distance. So do I have an equation that relates time, acceleration, and distance for a constant acceleration problem? Constant acceleration, so I'm back to this point in my chart. That brings me back to this. Nope, that's velocity. That's velocity. I want this one, don't I? Distance, time, acceleration. So this is the equation I want to use. It looks complex, but I think you're going to find it's going to simplify itself very easily. Let's write the equation down first. I'm going to bring this x to the left side because basically that's delta x. So I'm going to say delta x equals v initial delta t plus 1/2 a t delta t squared. Okay. I'm leaving out the subscripts x and y because of course we're only working in one direction anyway. Alright, so delta x is what I want to find. V initial, well that's easy because it's 0. I'm initially holding it still, so that whole term goes to 0, which is kind of nice. So this simplifies down to 1/2 a delta t squared. Now what am I solving for? I am solving for delta x. I don't need to do any why do I keep saying geometry? I don't need to do any algebraic rearranging. So let's just substitute in and solve. 1/2 times 9.8 meters per second squared. Delta t, remember I'm looking for how far does it fall in 0.1 seconds. And don't forget to square it, that's important. Units would cancel there, so let's plug it in and see what I get. 9.8 divided by 2 times 0.1 squared, 0.049 meters. My choices are in centimeters, so of course a meter has 100 centimeters. Multiplied by 100, and what am I left with? 4.9. So the answer should be B, and that is correct.